All right, good evening, everyone. Welcome to our BUILD-12 mission presentation, part of the NASA L-Space Mission Concept Academy. I'm Nick Florio.
I'm Sebastian Perez Lopez.
I'm Chase Weinberger.
I'm Joe Faso.
I'm Samir Parahar.
And I'm Juan Cortez.
And some of the other members could not be here tonight, but they worked especially hard on it as well.
So following NASA's Mars Exploration Program science goals, the BUILD-12 mission plans to touch on all 4 of the overarching goals for NASA's MEP, which are determining the possibility of past or present life on Mars, characterizing the climate of Mars, researching Martian geology, and preparing for future human exploration. This will be done with the active radiation and composition handling and inspection for true edifice component tracking lander, also known as Architect. Clay composition data collected by Architect will provide insight into Martian geology, ancient Martian climates, and past and present habitability. Radiation data will be used to study the Martian radiation climate, as well as shed light on potential risks for future human exploration. And finally, Architect's premier science objective will be compacting loose Martian regolith, which, when combined with data from the science payload on Architect, will be used by the science team to study brick feasibility and gain insight into Martian soil's viability as radiation protection.
So what drew us to this area of Northeast Syrtis was the high potential for science acquisition. Using CRISM data, we determined there to be a high presence of iron and magnesium clays, as well as aluminum clays. Also, this area is very smooth with an average slope of about 1 degree, as determined through high-rise and MOLA data sets. Lastly, this area is really homogeneous, meaning that no matter where we land, we're going to be able to conduct our science and reach our goals properly.
So the BUILD-12 entry vehicle uses an EDL process similar to other Mars missions like InSight, except for one major change. Given the large mass to area ratio of our mission, a rigid heat shield wouldn't be sufficient for entry. To lower this ratio, our EDL uses a hypersonic inflatable aerodynamic decelerator, or a HIAD. With our heat shield fully inflated, we will have a heat shield diameter of 1.4 meters. After peak deceleration, we will then deploy a 5-meter parachute. After some time has passed and we've slowed down to about 100 miles per hour, our lander will use 4 Flight Heritage retro rockets to slow ourselves down to a complete stop at the surface. So in order to carry out all of our science objectives, we utilize a robotic arm named Chester, which stands for Compaction Hardening and External Sample Testing Effector Arm. Chester has 4 degrees of freedom driven by stepper motors and has a reach of about 0.8 meters on the surface. After obtaining a sample with the scoop, Chester will analyze the sample with the APXS, then compact the sample. Both of these operations are driven by small linear actuators on the lower half of the lower arm. Finally, Chester can position the sample over the rad for long-term measurements.
To power all of this, we rely on 2 solar panel arrays that are attached to the sides of Architect. They are designed to produce 141 watts and can produce a maximum of 1,800 watt hours in a given 13-hour day. Its total surface area is 0.786 meters squared. It folds out like InSight's solar arrays and is based on the UltraFlex system that has been used at NASA previously. And excess solar energy that's captured throughout the day is stored in large battery tanks.
Just to capitalize on the electronics further, as you can see on the picture on the right, we are utilizing in our main electronics hub the RAD 750 flight computer, which is basically the brains for our lander, and that's provided by BAE Systems. We also have our RF electronics, our EPS, which includes converters and things of the sort, along with solar electronics, which can be paired with those solar panels, as Samir said earlier. And so, as you can see below, we also have our battery stack, and we have a redundant RF electronics.
To keep our lander operating throughout day and night, we rely on heating and cooling systems. Architect has 2 parts to its thermal system. The first part is a cooling system that uses the active heat rejection system to expel 150 watts of thermal power. The second part is the heating system that uses a GPHS, which is a nuclear thermal generator, to produce 250 watts of thermal power. And To move all of this around, Freon 11 coolant is used to regulate heat on the lander through a closed-loop feedback control system that uses various temperature sensors on the underside of the lander. With that, Architect will be able to operate throughout the day.
So then for our communication systems, we're utilizing a ultra-high frequency monopole antenna to receive and transmit data to and from the local comms package. And we're using a diplex arrangement for that. And in order to ensure that we can receive our science data here on Earth for further analysis and also send important instructions to our lander on Mars, we have an X-ray antenna, and as you can see on the picture below, and it's also blown up on the right, the front antenna is our redundant one, and then the main one is the one transmitting in the image.
So now we're going to move on to our science payload, and the first part of that is the APXS. NASA's alpha particle X-ray spectrometer uses two different sources of radiation to measure compositional spectra, and with APXS, Martian rock and regolith surfaces will be analyzed to determine their chemical composition. APXS's role in Architect's primary science objective will be to collect composition data on the soil that is being compacted. And with these measurements, the Architect science team will be able to study if variations in soil composition have an effect on how compacted Martian soil interacts with radiation. A JPL model of the APXS can be seen in the figure on the left, as well as our CAD model that was used for Architect's design below it. And you can also find a sample spectra obtained by a version of APXS in use on the Mars Science Laboratory on the right. So the second main part of our science payload is the Radiation Assessment Detector, or RAD for short, and it measures the makeup and amount of radiation traveling through the Martian atmosphere. RAD will be used to analyze the characteristics of Martian bricks and determine the validity of using Martian bricks as radiation protection for use in future human exploration. By taking RAD measurements both with and without compacted soil overtop the sensor, scientists will be able to compare the incoming radiation levels and study important changes that compacted soil may cause in the levels and makeup of incoming radiation. A picture of RAD along with the CAD model used for Architect's design can be found on the left, and an example of RAD measurements from the RAD on Mars Science Laboratory can be seen on the right.
Architect will be viewing the Martian landscape using NASA's Instrument Deployment Camera and Instrument Context Camera as a set of stereo cameras designed to acquire images of both the lander and its components, as well as the surrounding Martian surface. They are very similar in design to the previously used nav cams and HAZ cams, respectively. The IDC is a color camera mounted to the arm to provide images of Chester's workspace, while the ICC is a black and white camera that will sit stationary on Architect, providing vital information for deciding where around the lander to collect samples for APXS measurements. When coupled with IDC's stereo color images, scientists and engineers will be able to construct a 3D model of the Martian terrain in front of the lander. The budget was collaborated on by all members of the team. Prices for instruments were produced using NICM, since there are no specific prices publicly available. Instrument costs include the APXS, cameras, the RAD 750 computer, sensors, etc. The materials and supplies costs include cost estimations based on weights of parts of the lander and the materials used to make them. After accounting for margin, our project costs came in well under budget at about $90 million. The project schedule spans 4 years and is split into 5 phases. Orange bars represent our time to complete specific tasks, and green bars show our margin for completing them. We set ourselves up to dedicate more time to the design and testing of the HIAD system, a relatively newer heat shield. Full integration and testing will proceed up until launch in October 2024. Architect will land on Mars in June 2025, with data acquisition following through to October 2025.
Thank you.
Thank you, L Space
Thank
family.
you, Space.
Thank you.
And a special thank
Thank
you
you.
to our mentor, Hannah. And be sure to follow our Twitter at build_12 L Space. Thank you.